Welcome back. This is number 4, video number 4. My name is Ari Borestiano. We are going to talk today, we take it one step further. We are going to talk about the Minkowski sum, but we are going to tie it with this concept called support functions. Okay, the support function is a concept that is not used just for, to talk about Minkowski sum. We are going to relate it to Minkowski sum, but support function is a way to describe properties of convex set. So let's start with the definition. So let K be K, capital K, be, for simplicity, a compact, convex, we can generalize, but convex subset of R D. Okay, so we are not confusing letters. Okay. The support function, which we always use H, sub-indexed by K, so it is support function of the set K, evaluated at U, which I will tell you in a minute what it is the supremum, okay, over all the X in K, okay, of the inner product between U and X. Okay, it's the inner product in RD. And the U, this function is defined for all U in R, use RD. Okay, so it's a function from RD to R. Okay, now it's a definition, and we can talk about its properties and things that it satisfies. But maybe just a picture will help us understand how what it does and what it measures, really. So again, I'll use R2, and we'll get certain set K. Okay, so suppose this is our K. Okay, this is K. And a support function, okay, is going to measure how far can I go in each direction. So for understanding that, one first property that we need to remember about the support function is that the HK, okay, of, and I pick some lambda number, lambda U, is equal to lambda time HK of U. Okay, so if I multiply U by lambda, it's a stretch. It's going to stretch the support function by the same factor exactly. Therefore, usually, instead of looking at all vectors in RD, we can normalize to vectors of length 1. If the length is longer than 1, we can just multiply by the length of the vector and inflate. Okay, so instead of all the vectors in RD, we usually think about U in the unit sphere. Okay, the unit sphere of dimension D is written with S, fancy S, and D minus 1 because it's not a full ball, but just a unit sphere. Okay, so we will go rotate, okay, around the unit sphere in R2 is just a unit circle. And we will look in all directions, and we will see how far can we push a line that will be normal or perpendicular to the direction that we are looking away from the origin. So for example, if I'm looking in this direction, okay, this is a direction on the unit ball. The unit ball is somewhere like this. And I'm going in this direction. I can push a line, push a line, push a line until I will be like that. And that's measure of how far the set is from the origin in that direction. And I will do it in all directions, and I can draw a convex set using the support function. Okay? So to understand more about the support function, and we will reach at the end the punchline that relates it to Minkowski sum and its important property. Apart from this property, we can also say that, okay, h of k and we look at sum of two directions. This is not Minkowski sum. This is just two vectors in R2 or RD, or on the unit sphere. Okay, it is sublinear. Okay, which means that it is less or equal to K V. Okay, and those are regular sum, not Minkowski sum. We didn't reach Minkowski sum yet. Okay, so that's one good. And another properties of the support function, it has a lot, but I'll go over a few important ones, is that it's what we called, it's monotonic in a sense that if a set K is a subset of another set, let's call it L, okay, then in each direction, HK U is less or equal than HL in that direction. Okay, all seems, of course, if the set is bigger, then we might be able to push the line further because L is a bigger set and K, it includes K. Okay, those seem very good. The other thing, and that's more for convex analysis, the other property, the fourth one in our counting here, okay, is that if K is convex, okay, and that's what we are going to work on, K convex, okay, then we can write K as the intersection of all those supporting, okay, lines. And if we have infinite number of them, we will redraw, okay, if I tilt that line continuously around the circle, I will draw the points where it touches. We'll draw back the shape, okay? So we can say that K, okay, can be written as, okay, the intersection of all the half spaces. So I take everything that is below this line, and then I draw another line, everything below it, and I intersect and intersect, okay? And I take the intersection of all x's, okay? I take the set X such that the inner product of X and U, okay? I think I wrote UX, XU doesn't matter. It's okay, we can change the order here. Is less or equal than HK, okay, evaluated at U, okay? And we will take the intersection of all the U. Here again, we can just take the unit sphere. Okay, so rotate over the circle, take all the half spaces below the supporting lines, intersect them, you redraw the shape. Okay. There is another property, a little bit less crucial, but it's good to know that it's a well-behaved function. So we will say that H, okay, the support function HK, okay, as a function is Lipschitz. Okay. Lipschitz continuous, and we can bound the constant for the Lipschitz is it depends on where that set is, how big it is, and how far away it is from the origin. But that's less important for us. So here is the punchline. Here, the important property that connects between the support function and the Minkowski sum. Okay, so I'm going to write it up here instead of down. So property number 6, which is the important one, is that if I have K and L, two sets, and again, to avoid things, let's say two sets, what I mean is compact, okay, and convex. Okay, I'll keep maintaining that compactness and convexity. Okay, and I look at the Minkowski sum of them, which will also, as you saw in the first video, will be a compact and convex set. Then the support function of K Minkowski sum L at any direction U, and U will be taken from the unit sphere, for example, is equal to HK U plus, and this is a regular plus, again, because those are numbers, HL of U. Okay? So why is that important? Okay, apart from being nice, again, we can generalize this to a sum of more than two sets. Okay, so think about a sample. I have I'll just have sets, okay, A1 to AN. This is a sample of sets randomly drawn or computed from some samples that we have. Okay, we take the 1 over n Minkowski sum. I goes from 1 to n of AI. Okay, so that's the Minkowski average of the sets. The support function, okay, of this will be this equal to, okay, to the average of the support function. So let's write this, which is again just an extension of what we already wrote. So let's call this, just for simplicity, A bar, okay, instead of, okay. So the age of A bar, which is a compact convex set, evaluated at direction U, okay, will be, okay, age of AI evaluated at a point U bar over this. So we'll sum over these quantities, divide by n, so we'll take average of them. Okay? And that's a useful and nice result that relates the support function and the Minkowski sum. And there are more properties and important things to say about the support function, and perhaps I'll make another video about it, but for today, this is, I would like to finish with these nice results about the connection between the two concepts. Thank you for watching.